All right, we're going to start chapter 5 by getting just some definitions down, talking about what, because you're going to be asked to find critical points throughout this chapter. So we need to know what a critical point of a function is. All right, so let's identify that, or just critical points. All right, the first kind of critical points are the endpoints of a function if it has one. So the endpoints, if the domain is a closed interval. All right, so if the domain is closed, those endpoints fall into the category of being one of the critical points. All right, the next kind of critical point are extreme values or extreme points. Extreme values would be the highest and the lowest of a given area within the function. It doesn't have to be absolute. There's a difference between relative and maximum, but these are maxes and mins. So within extreme values, you could have a function that maybe looks like this. Okay, and we would say that that has two maxes. Now the maxes have a different adjective to describe each of them, but this would be counted as, oops, let's change color on that. This one would be considered a max, and this would be considered a max. All right, we can call this a local or a relative max. And then the higher of the two maxes would be called an absolute max. So, I mean, you think of it like, you could say, you know, I'm the oldest person in this classroom, but I'm not the oldest person at this school, right? So, within a small area, I am the maximum, okay, but if you take the bigger area, I'm not anymore. There's someone else older than me, something like that. You could do that with minimums as well. A maximum could be an endpoint. So, if the function was closed, and you had a closed interval like this, you'd have, again, two maxes. The endpoints would be the maxes, but the lower one would be considered the local or the relative, and then the absolute. Whereas this would just have one minimum. Oh, another word for absolute is global. The global max, that just means the universal, that, you know, the one that's highest of all. All right, other critical points. Critical points also happen where there are horizontal tangents. That's where the derivative comes into play, because you're going to set the derivative equal to 0. Now you might think, well, isn't that just an extreme max or min? Won't we have, yes, but there's also places where you have a horizontal tangent and you don't have an extreme max or min. So we want to say here we're going to set dy dx equal to 0. So of course, this would happen on a parabola at its max or at its min. For sure, that would be horizontal. But it would also happen on a cubic. For example, a cubic might look like this, and it has a horizontal tangent for a very brief moment right there. Now it has a horizontal tangent, but it's not a max or a min. There's going to be a special name for that point in a future lesson, but for now we're just going to call that a stationary point. So it has a horizontal tangent, but it's not a maximum or a minimum. So we consider that a stationary point, but we're going to give it a formal name later. And then the last kind of critical points are the vertical tangents. And the vertical tangents come from setting the derivative equal to undefined. You saw one of those in your tests in chapter 4. So we'll set the derivative equal to there. Okay, that might be like a cube root function or something that looks like this, or maybe an inverse trig function, and it has a vertical tangent right there. That would be considered a critical point as well. So when you are asked to find critical points, you need to consider all 4 of those categories. Okay, so any questions so far? There is something called the extreme value theorem. Okay, the extreme value theorem says this: you'll always be able to find a max or a min, a max and a min, if, there's always the if. Okay, you can't just stop a theorem and say you'll always be able to find a max or a min. You can't just stop there. You'll always be able to find a max and a min of a function if the function is continuous and closed, on a closed interval. All right, so let's record that. Okay, you can always find an absolute max or min I keep saying or, it's and. A max and a min if f of x is continuous and on a closed interval. All right, that is called the EVT, or the extreme value theorem. You will be asked more often not to actually find the max or min, but to say if it's possible. Is it possible to find a max of such and such a function? And you're going to answer yes or no and then justify. Yes, because it's continuous and it's on a closed interval. If you just have the continuity part, then you're not guaranteed. Does that mean the max or min doesn't exist? No, it might, but you're not guaranteed that it would be. It must be true if it's continuous and closed. That's called the extreme value theorem. All right, so let us practice. Identify the critical points for the following function. And the function is f of x being equal to x cubed minus 75x plus 100 on the interval 0 to 6 open. So however you think about it, just think you got to cover all four bases. Okay, you got to cover endpoints. If there's parts of the, for the interval, even if one of them is closed and the other is open, then you got to check the closed one. You got to cover maxes and mins. You got to cover horizontal tangents. You got to cover vertical tangents, and you're going to do all that without a calculator. Okay, so however you think of it, if you think of it like the branch, the four things going down this way, or if you think of it linearly like a list, boom, 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 I got to do these things. Okay. All right, so let's do our endpoints first. So the endpoints would be f of 0 and then f of 6. Those are the two ends of the interval. F of 6 does not exist because it's an open interval. F of 0, okay, I don't need a calculator to plug that in. What do I get? Anybody? 100. Okay, very good. All right, so I found a critical point. I've got one. Okay, now, maxes and mins. I can cover maxes and mins by doing horizontal tangents. Okay, so maxes and mins is like a subcategory of horizontal tangents. Horizontal tangents can find you maxes, mins, and stationary points all at the same time. So I'm just going to do skip to the horizontal tangent part because it'll find me the maxes and the mins. Okay, all right, so let's do horizontal tangent. To find the horizontal tangent, I am going to find the derivative, f prime of x, which is 3x squared minus 75, and I'm going to set that equal to 0. I'm going to solve that by factoring. So I get 3 factored out of x squared minus 25. So that'll be 3x minus 5 and x plus 5. And so I get 5 and negative 5. So now I need to find the function values at both of those places. Okay, f of 5 and f of negative 5. So I found the x values, but I still got to find the y values. Okay, f of 5, we can again do some mental math. So we'll have 5 cubed minus 75 times 5 plus 100. So 5 cubed, 125. Minus, do you guys know what 75 times 5 is? Do you know what 75 times 2 is? 75 times 2 is 150. So 75 times 4 would be 300. And then you got another 75 on top of that. Okay. So 375 plus 100. So 125 minus 375 plus 100. So it's negative 250 plus 100. So negative 150. Okay, f of negative 5. Now I could spend the mental energy to plug negative 5 in, but remember what our domain was. Our domain is where to where? 0 to 6. So I don't need to spend the mental energy to do that because it's not in the domain. Okay. All right, so then we can move on to 3. Vertical tangents. So we again take our f prime, which we previously found, 3x squared minus 75. We set that equal to 1 over 0. Drop 1 under the 3x squared minus 75, cross multiply. You get 1 equals 0, which is a false statement. And so this function has no vertical tangents. So what I got from all of that were 2 values. I got one endpoint, and then I got another critical value of f of 5. And so I have my results, my summary, is I had f of 0, which was 100, and I had f of 5, which was negative 150. And those are the only 2 I had. And so one of them is the maximum, and one of them is the minimum, and you can tell by the y values which is which. And so we've got our max, and we have our min. So if you have multiple points, if you end up with more than 2, then you're going to have to, for your absolute max, you got to take the max of the maxes. And if there are more than one low number, you'll have to take the lowest as your absolute. The other ones would be relative or local. Okay, let's try another one. Okay, so similar thing. Find the critical points. For the following, f of x being equal to x to the 2/3, and this time on the fully closed interval from negative 2 to 3. And so you can kind of think through, all right, my endpoints. I have a completely closed interval, so I'll need to think of what f of negative 2 is and what f of 3 is. So negative 2 to the 2/3 and 3 to the 2/3. So what that means, negative 2 to the 2/3 means the cube root of 4. And 3 to the 2/3 is the cube root of 9. One is clearly higher than the other. Okay, horizontal tangents. We'll take our derivative. f prime. The derivative of x to the 2/3 is 2/3 x to the negative 1/3, which written in a more user-friendly way is 2 over 3 cube root x. I will set that equal to 0, preferably over 1. I'll cross multiply. I get 0 equals 2, which is a false statement, so there are no horizontal tangents. And then the last step would be finding vertical tangents. So we'll go back to our derivative, f prime of x. We'll set that equal to 2 over 3 cube root x. We'll set it equal to 1 over 0. This time when I cross multiply, I get 3 cube root x equals 0. And that is something you can solve. So the cube root of x must be equal to 0. And if you cube both sides, x is equal to 0. So I get a valid, and it is within my interval. And so then I need to find what f of 0 is. So f of 0 is 0 to the 2/3, which is 0. So my summary, I had f of negative 2, I have f of 0, and I have f of 3. Negative 2 was the cube root of 4, 0 was 0, and 3 was the cube root of 9. Which means I have identified my min as the 0, because it's the lowest value, and my absolute max is f of 3, because it has a higher value than the cube root of 4. Okay, this also works on piecewise functions. So if we wanted to find the critical points of g of x, which would be maybe defined as piecewise way. So 5 minus 2x squared and x plus 2, where the domain split at 1. So your endpoints here are the ends of the intervals. You need to check 1 minus, and you need to check 1 plus. And so our endpoints would be what g of, say, 1 minus is, and what g of 1 plus is. G of 1 minus is 5 minus 2. That's equal to 3, and that's a closed value. It's closed because the interval had the less than or equal to bar underneath it. 1 plus, I'm going to get 1 plus 2. That's also equal to 3. So technically that's open, but since both of them have the same value, what do we say about, this is like checking the limits, right? So what do you know about this piecewise function? It's continuous, okay? And at this juncture point. Okay, for horizontal tangents, you're going to have to check both pieces because there could be horizontal tangents in each piece. So you'll have to check the derivative of the top piece and the derivative of the bottom piece. The derivative of the top piece is negative 4x. Set that equal to 0. The derivative of the bottom piece is just 1. Set that equal to 0. So the bottom piece doesn't have any horizontal tangents, which would make sense to you because it's a line, and lines don't have horizontal tangents. But the top piece was a parabola, and it will have a horizontal tangent at 0. So now I need to check what g of 0 is. G of 0 is 5 minus 2 times 0 squared, or 5. And then the last step would be checking vertical tangents. Again, you would take your same derivatives and set them equal to 1 over 0. You'll get good at this. Of course, a line doesn't have any vertical tangents either, neither does a parabola, so we have no vertical tangent. So our summary was g of 1, which was equal to 3, and g of 0, which is equal to 5. And so you have your min and your max.